Okay. Okay. Welcome everyone to the first eCHT research seminar of 2024. We're very happy to have Tyler Lawson from the University of Minnesota, who will tell us about filtrations and spectral sequences for structured algebras.
Right. Thank you so much, everybody, for bearing with me, and I apologize for running late. So today what I want to do is I want to talk about some structures on filtrations and stable homotopy theory. So given a tower of spectra, so a filtration that decreases, we get a spectral sequence that tries to compute the homotopy groups, and it has this kind of general shape. We take the homotopy groups of the quotients using some goofy indexing convention that we inherited from Serre, and then that tries to compute the homotopy groups of the final object in the tower. And different filtrations on an individual object can give different perspectives on X. So some properties of this is that we have different kinds of elements in this spectral sequence. Some elements are permanent cycles, and those mean that they persist and eventually contribute to being elements in the homotopy groups of X. Some elements are targets of differentials, and that means that at some stage in the filtration, we have an element that eventually becomes zero as we pass to lower filtrations. And it tells us about a relation that's true between elements in the homotopy groups of X. And some elements, by contrast, are sources of differentials. They don't actually become elements in the homotopy groups of X, but they enforce the above relations. And kind of working with those and finding with those is part of learning to work effectively with these types of calculational tools. The kind of famous spectral sequence that we have is the atom spectral sequence. So an atom's tower is constructed in a particular way. Each of the individual quotients of one stage by the next is supposed to be a module over the Eilenberg-MacLane spectrum for mod P homology. So it breaks up as a product of Eilenberg-MacLane spaces. And we also ask that the composites from one stage to the next to its mod P homology are null, or equivalently that the map from xs plus 1 to xs is 0 on mod P homology. So if we take the fiber of the map from the sphere spectrum to the Eilenberg-MacLane spectrum and call that J, and think of it as an ideal, then one way to construct an atom's tower is to take X and smash it with iteratively higher and higher powers of this ideal. And one way to think about the atom spectral sequence is to say that multiplication by elements in this ideal is supposed to increase filtration. That's kind of a module theoretic way to think about the way that the atom spectral sequence works. And this is a universal description of the atom's filtration on the level of kind of filtered modules, modules over the sphere spectrum that have an inverse filtration. By contrast, there's another derivation of the atom spectral sequence that's more kind of in touch with the way multiplication works, and it's by the so-called Kobar construction. So what we do is we take a spectrum X and we smash it with higher and higher powers of the Eilenberg-MacLane spectrum H. So H smash X, H smash H smash X, and so on and so on. And there are various maps between them. The maps drawn in the picture given by unit maps, including from a new copy of the Eilenberg-MacLane spectrum, and there are also multiplication maps that aren't drawn that go in the opposite direction. And altogether, those give us a co-simplicial spectrum, and there's a recipe for taking one of those and producing a tower, producing a filtered spectrum. In terms of the tote tower, we're instead kind of not quite taking the tote tower, we're taking fibers of the map from X to the tote tower, but it has the same spectral sequence kind of construction. And this has a particularly nice effect when we start with a commutative algebra, a commutative ring spectrum or a commutative algebra spectrum. The result, the Kobar construction, is actually a diagram of commutative algebras. All the maps are maps of commutative algebras and so on and so on. And in the category of commutative algebras, we could instead write it this way. For commutative algebras, the smash product of them is their coproduct in the category of commutative algebras. So H smash R on the left-hand side is actually the coproduct, H coproduct R in the category. And similarly for the higher and higher stages. And so in these terms, one way we could think about this is that the evaluation at 0 thing, dropping down and telling us about the 0th part of the associated graded, that has a left adjoint, and the Kobar construction is the result of the left adjoint. That's kind of going fast, but thematically what it's saying is that if I've got a filtered thing and grading 0 has a map from H, this is in a certain sense a universal way to produce a tower so that grading 0 has a map of algebras from H. And so that's a universal property type description of the Adams filtration if we work in the category of cosimplicial commutative algebras. All right. So what I want to do is I want to talk about the way that this filtration interacts with multiplication. So multiplication, in particular, commutative multiplication in stable homotopy theory has a graded commutative multiplication. If we take a product of two things, we typically have a Koszul sign rule where that's equal to the product in the opposite order, where we multiply by -1 to the product of their degree. So odd degree elements anti-commute and everything else commutes with each other. I'm using a cup product type notation where I would usually be too lazy to write down the a symbol for the product, but this will be important for kind of remembering things later. Usually we don't have actual equality in commutative. We don't usually have x times y is equal to y times x. We usually have a homotopy between those. We almost never have equality in homotopy theory. And choosing those types of homotopies is part of having a structured commutative object. So if I talk about structured ring spectra, I'm obligated to write down these kinds of diagrams. I've got a product, x times y, and I could also write down the product, y times x. There's a homotopy between those, a path of different products that starts at x times y and ends at y times x. And we typically give that path a name. It's called the cup 1 product, x cup 1 y. For the opposite direction, there's also a path in the opposite direction, which is given by the cup 1 product of y with x, because choosing that path is part of the structure. And these two produce a loop in the space of multiplication of products of x and y. We could ask then for that loop to be filled in, to fill into a disk. That's called a cup 2 product, and so on and so on and so on. So all of these are part of structured commutativity, and if I'm honest, there are signs here that I don't really want to talk about, but I'll leave that for now. When we take x and y to be the same, this means that we get a bunch of self operations on an element, for example, an element in a homotopy. So the primary one is when we multiply x by itself and we get its square. The second one is a path that goes from x times itself to plus or minus x times itself, and that's called the cup 1 product. And it does different things depending on the degree of x. If x is an even degree, then this is a homotopy from x squared to x squared. It's actually a loop, and so it produces a new homotopy element that's hopped up in degree by 1. It's called the cup 1 square. Whereas if x is in odd degree, what the cup 1 square q1 of x does is a null homotopy. It has a job. It's supposed to enforce the relation that 2x squared is equal to 0 if x is an element in odd degree. The next one is the cup 2 product, and the way it behaves depends on the degree of x mod 4. And for example, if x is in degree 2 mod 4, then we get a null homotopy of this particular class, eta x squared plus 2 times the cup 1 square of x. And so on and so on and so on. There's a higher and higher sequence of higher cup I products. They all have individual jobs, and describing exactly what those do takes a bunch of work involving calculations with stunted projective spaces. And so we might like to ask, how does this structured multiplication, how does multiplication interact with the Adams spectral sequence? The most basic property it has is that the product itself, multiplying two elements, adds filtration. So if x is an element in filtration S and y is an element in filtration T, then their product, x times y, typically has filtration S plus T. But it might be higher than that. It might accidentally fall into higher and higher filtrations. And even better, if we have an algebra that has the structure of a filtered algebra, then there's an Adams tower that, if R is an algebra, there's an Adams tower that's a filtered algebra, meaning that there are multiplication maps of spectra, something from the S filtration and something in the T filtration multiply together to give something in the S plus T filtration. And so we'd like to ask, how does this interact with commutativity? The strongest possibility we could ask for would be something called a filtered commutative algebra. So a filtered commutative algebra is something, normally when we have a commutative multiplication, we have multiplication maps where I can take D things and multiply them together, and that factors through the action of the symmetric group. So that would give a map from this left-hand side called an extended power construction, taking the D-fold smash product and modding out by the symmetric group that maps back to R. And a filtered commutative algebra would also make this compatible with adding filtrations. If I take an element in filtration S and another element in filtration S and multiply them all together and mod out by the symmetric group, that should land in D times S, D times the filtration. And one consequence of that would be that if we have a filtered commutative algebra, then the spectral sequence has a gradative commutative multiplication, and it starts being gradative commutative at the E1 page. And unfortunately, the Adams tower simply doesn't and cannot satisfy this. The Adams tower comes from a cosimplicial commutative algebra. And if we have a cosimplicial algebra, we can construct this tower. That's a tower of spectra, and that gives us a filtered algebra, but it doesn't necessarily give us a filtered commutative algebra. And this is part of something in homotopy theory called the Dold-Kahn correspondence not being symmetric monoidal, and it's annoying, and it's really annoying. And so we might ask, we have these modern foundations for stable homotopy theory where we can do everything with infinity categories, and a lot of these point set discussions become not as much of a problem anymore. And so we could ask if this is repaired by the Dold-Kahn correspondence, if this Dold-Kahn correspondence is repaired by using modern foundations. And in fact, I would argue that the opposite is the case. So we don't have any improved version of the Dold-Kahn correspondence, but there are also more stronger variants of the Dold-Kahn correspondence that we can ask the same questions about, and we still don't have answers for a lot of those questions. So it is kind of an unpleasant circumstance, but it kind of is what it is.
Can I ask a question here?
Yes.
So about this, this failure of commutativity. I mean, so I sort of agree that it's important. I mean, the way I would think of it is in things like symmetric Massey products or total brackets, things of the form like X bracket X comma Y comma X. Like in a fully commutative situation, those things have to vanish. But we know that those things don't vanish in so isn't that like a proof that commutativity can't occur? Like it can't be fixed.
Right. So there's layers to being strict. So what I would argue is that if we have let me get to that in a slide or two, maybe that'll answer your question. Okay. So let's talk about what Robert Brunner's work. So Brunner developed a theory of power operations in the atom spectral sequence that kind of tells us what structure we really do get when we start with a cosimplicial commutative algebra. It's in the lecture notes in mathematics H infinity book. So if we've got a cosimplicial commutative algebra, and we've got two elements, X and Y, in filtration T, then their product is in filtration S plus T. That's additivity for the product. But their cup one product, the path that tells us X, Y, and YX are basically the same, doesn't lift to filtration S plus T. It does lift to filtration S plus T plus minus 1. It lifts one stage lower. And there are further and further variants of this. One thing we find as a consequence is that the products XY and YX are not the same when we look at them on the E1 page, but after turning the page in the spectral sequence, they do become the same. So more generally, there's statements about what happens with the cup 2 product, the cup 3 product, and all the non-binary products that are non-binary in the sense of being not products of two things, not something else. There are things about products of iterative things as well. And so let me think about this by drawing a picture. Here, I've got a spectral sequence and I've got a class X that's in total degree 3 and filtration S. If I had a filtered commutative algebra, then the first class I get is X squared. And then there's a cup 1 square, Q1, and a cup 2 square, Q2, and so on and so on and so on. All of these might be elements in homotopy, like the cup 1 square might be a new homotopy element if X was an even degree, or these might instead be things that have jobs. So Q1 of X might have the job of killing off 2X squared. It might be a null homotopy. And similar for the higher and higher classes. And so if we have those in a filtered commutative algebra, all of those elements live in the same filtration as X squared. Whereas if we have a cosimplicial commutative algebra, those elements actually progressively live in lower and lower filtration. They don't lift to the same level. So far as symmetric Mazzi products going, Dan, to address your question, symmetric Mazzi products vanishing, that would be like something about products being, the higher products being actually trivial. Here I'm saying something about, they don't have to vanish because they homotopy theoretically don't vanish, but the symmetric Mazzi products might lie in a different filtration than we would expect if we had like strict commutativity. Does that kind of address what you were talking about?
Yeah, I think so.
Okay. Okay, so this is what we might see if we've got a cosimplicial commutative algebra. We start with the squaring operation. The cup1 square q1 of x drops 1 filtration down. The cup2 square drops 2 filtrations down. And those keep dropping filtration until we end up at the same filtration that x was in. And then the rest of the higher operations all live in the same filtration as well. So this is a consequence of what Brenner did. And there's also stuff at odd primes. Stuff at odd primes is harder to say because odd primes involve more stuff, but that's the basic idea. And for anybody in the peanut gallery following along, if you are into this synthetic approach to studying stable homotopy theory or thinking about spectral sequences, commutative objects in synthetic spectra actually have an even lower drop. The kind of higher power operations on X drop progressively into much lower filtration than even X appeared in the first place. So there are some major applications of this. So one of those applications is the Hopf invariant 1 problem. So the Hopf invariant 1 classes in the atom spectral sequence have particular names. We usually call them HI or H1, I, or maybe something else, depending on whether you've switched from using odd to using odd primary notation at the prime 2. These are a particularly interesting series of classes that answer questions of classical interest, and they are related to each other by this cup1 squared. Each of them is in degree 1, degree 3, degree 7, degree 15, and so on, and each of those is the cup1 square of the previous. And that means that these classes, because they're cup1 squares, they technically have jobs. Their job is to enforce the relation that twice the square of the previous one was supposed to be equal to 0. And so they have a tendency to survive the spectral sequence if and only if that class had another reason to be 0 in the first place. So for example, 2 times eta was already 0, 2 times h1 is 0, and so we don't need an extra object whose job is to kill 2h1 squared. That's automatic from the element itself being killed by 2. And so this is a kind of the heart of Adams's approach to proving the Hopf invariant 1 problem as opposed to the postcard K-theoretic proof. Similarly, the Curvarian variant classes are the squares of those classes, and they're related by a cup2 squaring operation in the atom spectral sequence. Mostly they are in degrees that are congruent to 2 mod 4. And so this means that if we've got a Curvaire class that survives, then the next Curvaire class has a job. It's supposed to be enforcing a relation that looks like this: eta times the previous 1 to the 4th plus twice the cup1 square of the previous 1 squared is equal to 0. And I don't want to get into it or talk about calculations about the cup1 square, but technically speaking, its job is really just to kill off eta times h1, hi to the 4th. And so it survives if this element is already 0 for some other reason. So this is at the heart of Mahowald's program to kind of take Curvaire classes and produce the next Curvaire classes by doing things like verifying that they satisfy relations. Now that program kind of failed because it turned out that the Curvaire classes don't survive, but that's kind of the idea of how you might produce some of them, and maybe someday somebody will figure out whether the final Curvaire class is still in the atom spectral sequence, possibly someone in the audience here. So there are a couple of takeaways that I want to give from this. So there's one type of commutativity when we were talking about commutativity for algebras, for objects in stable homotopy theory. But when we start to look at filtered objects, there's multiple different types of commutativity, different layers we could have. We could ask for stronger relationships or weaker relationships between an element X and its products and all these higher pieces of information that's satisfied. And with each type of structure, we get a different perspective. The one thing that would be nice would be if we had better control over these power operations in the atom spectral sequence and they did land in higher filtration so that they didn't have this strange thing. But having them go lower actually allows us to compute things about the Hopf invariant and covariant variant classes. So each different perspective assigns different weight, different priority to the same phenomenon. And so I want to say that there's not a correct way to look at these things, and looking at things differently could give us emphasize different aspects. Let me say what I mean by that. So we could instead talk about alternatives to the atom spectral sequence, different ways to take the sphere spectrum and compute things about it, or different ways to take another object X that compute things about it by not working with this Adams tower. We didn't get a commutative filtered algebra, and we could instead force that in multiple ways. We could take this universal property that the cosimplicial version of the atom spectral sequence satisfied and enforce that, but instead enforce that in the category of filtered algebras. I could say, I want to take the sphere and I want to turn it into a filtered algebra, and I want the 0th layer of that filtered algebra to be the Eilenberg-MacLean spectrum. I am informed by the younger homotopy theorists that this is the thing that one does with just some adjoint functor nonsense, but so it's possible to do so, and this gives a filtered object whose associated graded looks kind of like a free algebra on something called the topological Andrei-Quillen homology. So this is a little bit strange, but it's kind of a useful way to think about things in a way that deliberately pushes power operations into twice the filtration on the class that they were taking power operations on. We could also instead, rather than asking for this universal property, say, well, instead, I'm going to start with the sphere and I want to push an element into higher filtration. So if I've got a ring R and I've got an element X that's in filtration S, what I could do is I could take X and take a free filtered thing on a class into filtration S, and then I could deliberately take a push out to force that element to be in higher filtration. And then I could do that push out in the category of filtered commutative algebras. Or I could have done that in cosimplicial commutative algebras, or I could have done it in EN algebras for some n, and each of those has a slightly different behavior. It does different things to X, but it kind of enforces a relationship that we wanted in a designer way. It makes X less important by pushing it higher up, and also has consequences for various operations built out of X. And there are an abundance of different ways to do this, each of these having the goal of saying, let's take some computational piece of information that we wanted to know and tell us more about it. All right. So this leads me to talking about some joint work with Mike Hill, but this is based on some observations that were made in joint work with Agnes Baudry, Mike Hill, Denny Shi, and Mingkong Zhang. So what we did was we found a formula for calculating certain EK pushouts. Generally speaking, EK pushouts are horrible to calculate. I don't recommend it. They involve a lot of Lie bracket stuff. The algebras are I don't know, I find them kind of computationally intensive, and so I don't like doing that. But here we found some kind of general thing. I don't want to run over the allotted time, since I know that people's time is important, so I won't get into details about this. But the general idea is that if we've got an EK plus 1 algebra B, and we've got two EK algebras, A and R, that have various maps between them, we get a homotopy pushout diagram in the category of EK algebras over B. And this pushout in the lower right corner is a relative smash product. The interesting case that I'm going to be talking about is when B and R are both the sphere spectrum here. And so in that case, most of this simplifies a lot. This would say that if I take an EK algebra A and I want to take the push out of a map from A to the unit and a to the unit, that would be a relative smash product of the unit over this free ek+1 algebra with the unit. And so this would imply a consequence of the Hopkins-Mahowald theorem. The Hopkins-Mahowald theorem is a famous theorem that says that if I take the sphere spectrum and I kill off P, but I kill it off in the category of E2 algebras, I get the mod P Eilenberg-MacLane spectrum. What this does is this says, well, instead I could turn that push out, that thing that killed off P in an E2 way, I could turn that into a relative smash product over a free E3 algebra. So the Eilenberg-MacLane spectrum can be identified with the sphere spectrum smashed over the E3 algebra on the sphere with the sphere. This is a kind of odd way to view it. And what we can do with this is we could use it and we could say, I want to engage in this pushing technique. I want to take the sphere spectrum. I want to take the element P and I want to say, let's push P into filtration 1. How I'm going to do that is I'm going to take this diagram of little free algebras. I'm going to take a free algebra on an element in filtration 0, mapping to detect P, and I'm going to take a push out, but I'm going to do it by smashing these. I'm going to take this free thing on a element in filtration 0 and a free element on filtration. So this algebra W kind of has a universal property. It's a relative smash product, and we could say it in the following way. We start with the sphere spectrum, concentrated in degree 0. We take P and we push it into filtration 1. We do it in a category of filtered E2 algebras, and we ensure that this lift of P stays central, that it still stays commuting with everything. That's kind of the property of being a left module over this free E3 algebra. That ties into the so-called center of an algebra that appears in the higher algebra. So this is weird and specific. Why did I pick 3? Why did I, deliberately do things with this relative smash product rather than just doing a push out? So why would I engage in this specific technique? And the reason it's so specific is that among the types of techniques you could do for pushing P into higher filtration, this results in a particularly small calculation. When we do this, for example, at the prime 2, the spectral sequence that calculates the stable homotopy groups of spheres and starts with the associated graded of this filtered E2 algebra is a polynomial algebra. It's a polynomial algebra where you take a class X, which is where 2 got pushed into filtration 1, and you start applying power operations to it. You've got these Q2 power operations and Q1 power operations. Each of those power operations doubles filtration and has a specific effect on the total degree. So if you calculate things out, the filtration of this power operation is 2 to the k plus L, and it's got this total degree. And it's convenient for notational reasons to change notation slightly. I'm going to call these script Hij, where I is greater than or equal to 1 and j is greater than or equal to 0. Each of those has filtration 2 to the I plus j minus 1, and they're in total degree 2 to the I plus j minus 2 to the j minus 1. And the only reason I would do that is it suggests a relationship with another spectral sequence that we already had out there in the world. There is a thing called the May spectral sequence. The May spectral sequence's job is to compute the E2 term of the atom spectral sequence, and it starts with polynomial generators that are in these same degrees, but quite different filtrations. And there's a similar relationship at odd primes. If I do this at odd primes, I get a polynomial algebra tensored with an exterior algebra, as one does, on classes that one might call BI, J, and HI, but it's has the same kind of connective tissue with the May spectral sequence. It has the same total degrees, but wildly different filtrations. And this spectral sequence also, by contrast with the May spectral sequence, computes the stable homotopy groups of spheres directly rather than computing the atom's E2 term. So this is a different way to compute the stable homotopy groups of spheres, and it has the property that it's geared to push power operations into higher degrees. This cup 1 product is always pushed into twice the degree, the same degree as x squared is in. And so one of the ways we have a consequence of this is that we have differentials that are kind of very strange from either the Adams perspective or from the May perspective. These are D1 differentials. And they say that D1 of the HI plus 1 zeros is H10 HI1. Most of the HI1s get sent to 0 by the differential, and the other ones map to H10 times 2Hij squared. So some of these might look familiar. The top ones look kind of like the differentials you would expect in the May spectral sequence. If you look at the May spectral sequence, the May differential on HI plus 1, 0 would usually have more terms, but the rest of those terms have kind of been shoved into higher filtration and we don't see them. The bottoms differentials are things that we would usually see as Adams D2s. And they come from the fact that each of these HI comma J plus 1s, they are cup 1 squares. And so they have a job. Their job is to kill twice the square of the previous one. So it's very strange. By contrast with the Adams spectral sequence, we end up with weird and strange calculational properties of these. So for example, the Hopf-Covariant classes end up in unpredictable places. Let's talk about that. So 2 is detected by this class script H10 that lives in filtration 1. The Hopf-Invariant element eta is still detected by script H11. Those are consistent with the way those appear in the Adams filtration, except eta is now in filtration 2 rather than filtration 1. That's reflective of the fact that eta is kind of a power operation on the element 2, and so it got pushed into a higher filtration. The element nu, the third stem Hopf-Invariant, is detected by a new class, script H21 plus script H11 H20, living in filtration 4. The May spectral sequence detects nu by a class called H21 straight up without this correction term that I've written in blue. It's in the wrong filtration. And so this is kind of detecting somehow that nu itself isn't really a power operation on eta in some way. And similarly, there's an even stranger relation that the Hopf-Invariant class sigma is detected by something that doesn't involve H31 at all, and it doesn't live in filtration 8. It breaks the pattern. It lives in filtration 6. So in this perspective, we've pushed these geometric power operations into high filtration, and instead what we're finding is that nu and sigma are being detected by stuff that would mainly be garbage, that would be in high filtration, that would be correction terms to the fact that nu and sigma aren't literally cup 1 squares of the previous classes. And so this indicates that the geometric power operation isn't fully sufficient to construct classes, not construction classes. All right, so that's the main part of what I wanted to get to. And so I'm gonna say I got a little flustered and I went through all my slides, in fact. So that's where I will stop for today. Thank you very much for